Hello, welcome back to my YouTube channel on Hello Engineers. A DC, direct current, motor is an electrical machine that converts electrical energy into mechanical energy. It operates based on the principles of electromagnetic induction and Fleming's left-hand rule. Here is a brief explanation of its working and key components. Stator. The stator is the stationary part of the motor that provides a magnetic field. It typically consists of permanent magnets or electromagnets arranged in a specific pattern. Rotor. The rotor is the rotating part of the motor. It contains a coil of wire known as the armature, which is connected to a commutator and brushes. The commutator helps in reversing the direction of current flow through the armature coil. Armature. The armature is a core made of iron laminations and is wound with multiple turns of insulated wire. When current flows through the armature coil, it produces a magnetic field. Commutator. The commutator is a cylindrical arrangement of copper segments insulated from each other. It is mounted on the rotor shaft and helps in reversing the direction of current flow in the armature coil as it rotates. Brushes. The brushes are carbon or graphite contacts that maintain electrical contact with the commutator segments. They supply current to the armature coil through the commutator. Working principle. When a DC voltage is applied to the motor, current flows through the brushes and commutator into the armature coil, creating a magnetic field. The interaction between the magnetic field of the stator and the magnetic field produced by the armature coil causes a torque on the rotor, initiating its rotation. As the rotor rotates, the commutator segments make contact with the brushes, reversing the direction of current in the armature coil. This ensures a continuous rotation in a specific direction. The rotation of the rotor continues as long as the DC voltage is applied, and the commutator reverses the current flow in the armature coil. Applications. DC motors find wide applications in various industries and devices due to their simplicity, controllability, and versatility. Some common applications include electric vehicles. DC motors are used in electric cars, bikes, and scooters to drive the wheels. Industrial machinery. They power conveyor belts, pumps, fans, and machine tools. Home appliances. DC motors are used in appliances like refrigerators, washing machines, and vacuum cleaners. Robotics. DC motors are commonly used in robotic systems for precise control of movement. Computer disk drives. They are used in hard disk drives to spin the disks and position the read-write heads. Overall, DC motors are widely used in various applications due to their reliable performance, ease of control, and ability to provide high torque at low speeds. Role of EMF in DC motors. Back EMF, electromotive force, plays a crucial role in the operation of a DC motor. It is an induced voltage that opposes the applied voltage and is generated due to the rotation of the armature coil in a magnetic field. The role of back EMF in a DC motor can be understood in the following details. Counteracting the applied voltage. When a DC voltage is applied to the motor, current flows through the armature coil, creating a magnetic field that interacts with the stator's magnetic field. As the armature rotates, it cuts through the magnetic lines of force, inducing a voltage in the armature coil. This induced voltage, known as back EMF, opposes the applied voltage. Regulating the motor speed. The magnitude of the back EMF is proportional to the speed of the motor. As the motor speeds up, the back EMF increases. This increase in back EMF reduces the net voltage across the armature coil, resulting in a decrease in the armature current. Consequently, the armature torque decreases, regulating the speed of the motor. Preventing excessive current flow. The back EMF counteracts the applied voltage, reducing the voltage difference across the armature coil. This, in turn, limits the current flowing through the motor. It acts as a self-regulating mechanism that prevents excessive current flow, protecting the motor from overheating and damage. Efficiency improvement. Back EMF contributes to the efficiency of the motor. As the motor speeds up, the back EMF increases, reducing the armature current. This leads to lower power losses due to less resistive heating in the armature coil and lower I2R losses, resulting in improved overall efficiency. Dynamic braking. Back EMF also plays a role in dynamic braking of a DC motor. When the supply voltage is removed suddenly, the motor continues to rotate due to its inertia. The rotating armature cuts through the magnetic field, generating a back EMF. This back EMF creates a current path in the opposite direction, which acts as a braking force, gradually slowing down the motor's rotation. In summary, the back EMF in a DC motor helps regulate the motor speed, limits the current flow, improves efficiency, and contributes to dynamic braking. It is an inherent characteristic of DC motors that allows for self-regulation and optimal performance.